Now that we've talked about segmentation architectures, let's talk about a technique that we can apply to the training of such a model, data augmentation. We saw earlier how we could feed in transformations of chest x-rays such that the classification label of each example stayed the same. Let's now look at how we can apply the same principle to segmentation with a couple of key differences. One key difference with data augmentation during segmentation is we now have a segmentation output. So when we rotate an input image by 90 degrees to produce a transformed input, we also need to rotate the output segmentations by 90 degrees to get our transformed output segmentation. The second difference is that we now have 3D volumes instead of 2D images, so the transformations have to apply to the whole 3D volume. With this, we almost have all of the pieces necessary to train our brain tumor segmentation model. The final thing we need to look at is the loss function. In our loss function, we want to be able to specify the error we should assign an example given the model prediction and the ground truth. Let's take a very simple example. In reality, we're going to have a much higher resolution image and we're going to be looking at a 3D volume, but our simple 2D example here will allow us to get a quick intuition. Here, capital P represents the output of the segmentation model on 9 pixels, where at each location we have the predicted probability of tumor. Capital G specifies the ground truth on each of these pixel locations. 3 of the 9 pixels are tumor, represented as 1, and the remaining 6 are normal brain tissue, represented as 0.